Hello. This is a presentation on low temperature plasma jets. So this low temperature plasma jet, they are called non-equilibrium atmospheric uh, pressure plasma jets, acronym NAPPJs. The atmospheric pressure plasma jets, these are devices that can emit a cold plume of plasma, and they are used today extensively in biomedical application of plasmas. They're used for wound healing, in dermatology, cosmetic, and are under evaluation as devices for cancer therapies. So let's find what this cold plasma jets are all about. First, this is a picture of the plasma pencil. And you can see uh, a, um, a plume of cold plasma touching my hand, and and it doesn't, burn my skin or doesn't electrocute me or anything like that. It's very safe to use. The plasma pencil was the first biocompatible device that can emit plasma and that can treat cells and tissues. And we developed it, me and my research group, back in the early 2000s. Since then, there are many other configurations that were developed by other investigators, and these are some of them. The plasma pencil itself has a uh, ring electrodes that are attached to perforated ceramic discs, and the flow of the gas um, goes through the holes in the ceramic discs, and the plasma plume comes out into the surrounding environment, the surrounding air. These are, you can see two pictures there of the plasma pencil in operation. So we at the time in the early 2000s, we did not really understand how such cold plasma jets can be emitted in room air, because usually, if you want to generate such plasma in atmospheric pressure in room air, it they are extremely hot. The temperature will be several hundreds to several thousands degrees, so they are not biocompatible. So we wanted to understand how we actually can generate these plasma jets that are really cold to the touch. So we did some diagnostics, and then we discovered that these jets are actually sustained by guided ionization waves, and which came to be known as plasma bullets. You can see here some picture of the bullet that propagates from the time it's launched to the propagation phase, and then until it dies out a few centimeters away from the nozzle of the device. And it propagates at really high velocity. You can see here, these are, you know, tens of kilometers per second. Uh, the, uh, this ionization wave travels at hypersonic speeds. And of course, later on, it dies out because it propagates in air. And then you have diffusion of air into the usually helium or argon flow. And air has oxygen that attaches the electron and extinguishes the plasma. So in the next slide, I'm going to show you a, a movie of the propagation of this plasma bullet. Let me see here if I can play it. So this is how the plasma pencil looks like, and the plume, the naked eye. But in reality, you can see here after the plasma is ignited, you have this plasma ionization, this ionization wave propagating, which is looks kind of like a bullet, so they call it the plasma bullet. So I can play it one more time for you. So ignition of the plasma inside the tube, and then the propagation of the ionization wave or the plasma bullet. In this is air here. So we discovered that this is what's happening back in early around 2005, and then we published the paper in the scientific literature that explains the mechanism of propagation of this plasma bullet. So there are many applications of these plasma jets. It's called plasma jet. In biomedical application, for example, you can use them to inactivate bacteria. And you can see here in this images here, all these dark areas that you see, this is where the we aimed the plasma plume at this area here. This is a lawn of E. coli bacteria, and the dark areas here, that's where bacteria couldn't grow because it's been inactivated by the plasma plume of the plasma pencil. It, the surrounding here, the white area, this is where you have healthy lawn of E. coli that grew everywhere. So everywhere the plasma pencil touched, there is no growth of bacteria. So it shows you can inactivate bacteria. The, there is another way, for example, to use this plasma pencil is uh, uh, to treat a biological solution. So, and you can see here the plasma plume treating this pinkish looking liquid. And then you use the liquid that's been activated by the plasma. You can use it, for example, to treat cells like cancer cells. So yeah, show you an example here. And for example, we use this uh, epithelial cancer cells versus healthy cancer cells. And you can see here the dark gray, these are the cancer cells. And you can see that when they are treated by the plasma activated medium, which is called PAM, short for PAM. So they can see we after 4 minutes or so with PAM, treated for 4 minutes, we kill almost 90% of the cancer cells, while the healthy cells, basically up to 4 minutes, they uh, they are really not that much affected by the plasma, which is good since this shows selectivity of the plasma to kill cancer cells but not harm the healthy cells. Of course, if you have a long treatment time, then you also uh, hurt the healthy cells too. So that's it. I just wanted to show you the ad advantages of using this cold plasma jets for biomedical application.